Okay. I'm going to All right. Hello, everybody. I think we're live. For those of you who are joining or have been with us before, my colleague Neil is out today. So it's just me. And I would like to just get some feedback from those who are listening. Could you please type in the chat to let me know if you can hear me? Let me see. All right, so, okay, hello. It looks like there's a tremendous amount of feedback between, I know what I'm gonna do. Sorry, normally Neil handles all of the audio stuff, so I'm going to try and adjust this so that I can hear myself a little bit, and yet also kind of make sure that I can hear what's going on. Okay, but let me know. Can you all hear me? Give me some kind of sign in the chat. Hello, Kashif and George. Thank you for joining. Henri, thank you. Okay, great. Thank you. That's good to know. So first and foremost, welcome everybody to ask us anything about electrochemistry. This is from Pine Research Instrumentation. A couple just housekeeping things before we get started is that so normally my colleague Neil is with me. He also handles some of the technical stuff, but the goal here is just to try to answer as many questions as possible that you all may have about electrochemistry, and just have some healthy discussion about it, because electrochemistry is a very complex and complicated subject. So this live stream, I'm aiming for it to be about like 1 hour, maybe 2 hours, but we'll see. If there are not a lot of questions, I'll end early. If there's a lot of questions, I might try to give you a little bit more. Lastly, I'm using Zoom to broadcast this, so there tends to be a 20-minute delay between, or sorry, 20-second delay between when I see something in chat and when you hear a response from me. So just keep that in mind. That's what we've at least tested. And you can ask any and all questions. If you're watching this after the actual official live stream, I will try to have timestamps in the description to so you can at least even find your questions or other questions that you may have if you're watching this afterwards. Lastly, there are no dumb questions. And again, I apologize if I mispronounce anybody's name well in advance. Okay, so there are a couple of questions. Actually, I want to start off, it's not in the chat, but Matt Byung asked a question earlier. So if you actually have questions way ahead of time, you can just write a comment on any one of our YouTube videos, and if it warrants a further discussion on the live stream, then I'll do that. Also, because my colleague Neil is not here, he is more of the EIS person as well as the battery person. So he knows a lot more about those types of things than I do. But so if I can't give you really good answers with that, I apologize ahead of time. So Matt Byung asked a question, and that question has to do with the peak difference between the anodic and cathodic wave in the cyclic voltammogram. So if you give me 1 second, I'm just gonna close up a few things and make sure I share my screen. All right. So Matt was asking, Byung was asking, and I just want to, I always have to make sure my format is correct. Okay. So Matt Byung was asking the following question about the peak splitting between in a cyclic voltammogram. And don't worry, if you've asked questions in the chat, I will get to them. So normally when you have a traditional cyclic voltammogram of a reversible 1-electron redox couple, the difference between the anodic and cathodic waves tends to be about 59 millivolts. This number, this number of 59 comes from the Nernst equation. And so it's a theoretical, in many ways, it is a theoretical value. So, but you can get it. And Matt's question is actually, in the literature, he has found values that are not 59 that tend to be higher, somewhere between 59. I'm gonna just use the, I can't draw, like text is better. So this is, I had 59 here, 9 millivolts. And then he has observed in the literature that you get between 59 to even 120 millivolts peak separation. And this is peak separation. So the question is, why is this? Like, what's the discrepancy? So there's a few things. One is that getting 59 in all my years of doing electrochemistry of very well-behaved systems, I've almost never gotten exactly 59. Maybe I got 59 2 times. Experimentally, you will tend to find that you get numbers closer to like 60, 61, 62, 63, 70 millivolts. Some of these are all experimental things. It's that it's not theoretically this value. It's just in experimental practice, we get peak separations that are different. So that's one of the main reasons, is that experimentally we just run into this issue. The other thing, there are 2 things that, generally speaking, besides some experimental things that talk about the peak separation. One is solution resistance can cause it, solution resistance. And then the second thing, so that's number 1. The second thing is kinetics of your of redox couple. Okay, so these are really the 2 things, right? Within an experimental set, these are really the 2 things. The kinetics of a redox couple are usually pretty big. So if the oxidation and the reduction peaks are really separated quite a bit, and we have corrected for solution resistance, then the difference for a homogeneous redox couple is the fact that usually the rate constant or the diffusion coefficient is slow for this species. That is one reason why we would actually get a big difference in the peaks, because of the kinetics of the redox couple. I don't know if I have one with me, but there's actually a voltammogram of Tylenol, and Tylenol, acetaminophen, actually undergoes a 2-electron oxidation process. So you get this big peak, and then it's like over here, you end up seeing this reversible wave, hundreds and hundreds of millivolts apart from one another. And that has to do with the kinetics. It has to do with the chemical reaction that occurs. But the kinetics is one reason why you see this change in the peak separation. The last thing I want to mention is about the solution resistance. So I made a video about this, about IR compensation, that you can get these what happened right there? You can get these elongated voltammograms that are kind of stretched. They look a little bit more like this. And this is when solution resistance is high or not compensated for solution resistance, or uncompensated solution resistance. So this is how you can get these kind of big peak separations. And yeah, in the literature, you might not find people who actually talk about it. Let me also try to address Matt Byung's. See, thank you for addressing my question. Just a follow-up question. How can we be sure that the CV will always record 1 electron transfer? Can we know that just by looking at the peak? So that's a really good question. There are a couple of comments about the nature of electron transfer. So if there is a single electron transfer, we know what that looks like. In a sense, there's also, based on the equation, if you had a 2 electron transfer process, you would get, so let's just say you had another voltammogram. Again, I can't draw super well, but let's say that the peak splitting, if the peak splitting theoretically was about 30, that would be a 2 electron transfer process. The actual equation for the number of electrons, it's more like 59 millivolts per electron. So 59 millivolts per n, or number of electrons transferred. So this is number of electrons transferred. So this would cut in half if you had 2. Now, here's the interesting thing about electron transfer. Having 2 electrons transfer at the same time, I think, is actually very difficult. Like thermodynamically, 2 electrons at the same time transferring is very difficult. Most of the time, you get these, and especially at the same potential, right? So this is the potential, this is the current. Get 2 electrons to transfer, it's hard. What you tend to see most of the time is you get 1 electron transfer, and then you get like a second electron transfer at a more positive or negative potential, right? So electron transfers typically are concerted single electron transfers. That's typically what happens when you have a 2 electron transfer process. Of course, you can do experiments where there's multiple 2, 4, 6 electron transfers. They all happen in one area. Usually that's in a catalysis case. And that actually leads into another question, which has to do with a Tafel analysis. But let me just double check to make sure. Can we, let's see, to correct, let's see, can we know just by looking at, yeah, so Matt Bang, also just to kind of follow up and make sure I finish Matt Bang's question. Also, thank you, Kempor, for becoming a tier 1 member. Really appreciate it. To correct the solution resistance, can we add an arbitrary amount of supporting electrolyte? How much is too much? That is a very good question. So I actually don't know if there's quote too much electrolyte to a certain degree. Usually as people, as we start to add solutions, actually I can stop sharing. As we add solution or add electrolyte, it looks big. The amount of anolyte is super, super small. The amount of electrolyte's already pretty big. And you're like, okay, I'm going to just keep adding more to improve the conductivity, reduce the solution resistance. In some cases, it's very important that you add a lot. For example, THF, tetrahydrofuran, is extremely, extremely resistive as a solvent. And you would need to add a lot of supporting electrolyte to really bring down the resistance of your the solution resistance of your electrochemical system. I do recommend doing IR compensation, but yeah, I would say at max maybe one molar. I mean, it's a lot of electrolyte, but the system needs to be very resistive. And that being, I think there are other things you can do to remove this and correct for solution resistance. You can improve the distance between the working and reference electrode. That will decrease the solution resistance. You can also decrease the area of your working electrode because there's a current factor that's involved. And so if you decrease the current while still having the same chemistry, you will be able to get a lower IR drop. So hopefully those are some things that can help. I know I have like a whole video about the whole subject, but I think that's when you add so much electrolyte that other things are no longer possible, then you know you've added too much. I think that's the answer. Okay, so I'm gonna go back and I'm going to, hopefully that answers your question, Matt. You can continue to ask more. I'm gonna move on to another question. So George asks a question. He's doing cathodic disbondment, which is of a steel-coated panel, carbon steel-coated panels. And he wants to know if there's a way he can check the level of adhesion, or to check if adhesion between the coating and the panel has degraded, if there's an electrochemical test. So having not known that much about cathodic disbondment, to my knowledge, cathodic disbondment is breaking the adhesion layer between a coating and the sample. So honestly, I think there are a couple things you can do. One is electrochemical impedance spectroscopy, and I think a couple of people are asking some similar questions about electrochemical impedance spectroscopy. Gosh, I have a question about impedance spectroscopy, corrosion testing. Can surface area of protective barrier affect resistance of the barrier? I think I'll get to that a little bit later. But George, if your system has changed, I would imagine if a protective coating is missing, if the carbon steel coating on the panels is off, your EIS spectra will look very different, and the specific resistance values that you get will look very, very different. And EIS is very sensitive to those types of things. So you may have, Neil usually goes over some stuff like that. So let me just do a quick share of my screen. So one thing Neil commonly talks about when it comes to modeling an electrochemical system. So let's say you have your, I'm just imagining this is the electrode. And then you have your adhesion layer. So, or this is your layer. And what might happen in the event of some corrosion or some of the adhesion getting removed is you might get some areas where the layer is removed, right? So this is your coating. And so normally the way that this type of system is modeled is every time you have an interface. So if this is air, or actually no, if this is solution, sorry. If this is solution, we tend to model every interface as an RC circuit. So maybe you have some solution resistance, and then you have a resistor, and then a capacitor here, and then you have a resistor. Sorry, I should pick a different color. And then a capacitor here, sorry. And then your electrode. But here, if you actually had a different adhesion because you had cathodic disbondment, you would have your resistance. And actually I can make sure I don't make this mistake. I can change this to a different color. Oh, okay. So here, resistance, and then this. And sorry, keep drawing these things a little funky, but I think hopefully you get the idea. It's like we have the same thing, the interface, but then we also have this kind of interface here. And this is a capacitor. This is a resistor. I know I'm making these very close. These all go to the same path. So your EIS model, look for, see if I have any comments. But your EIS model will be different, and your results will be different if there is cathodic disbondment. So that is one thing you can do, and I think EIS is very sensitive, and that might be a way to check. So let's see if George had any follow-up. Oh, he did. Okay, so he did EIS, and he was just looking for something else. Will cyclic voltammetry give you something? So cyclic voltammetry, I think, will give you, I think it will give you some insight. It will look different when there's a coating and then there's not a coating. I think you will get something different in the cyclic voltammogram. It's just I don't know what what it would look like or what it would be. But you could definitely do compare and contrast between a fully, a system that has the full adhesion layer and one that might have some adhesion that's off of it. So yeah, I might do it. I might do it that way if your surfaces are different. You can also just another thought, but if you added an analyte that gives you a response in one situation, so something like a very well characterized electrochemical system is ruthenium hexamine. If you added that to your system and it gives you a response under one condition, you may notice the current associated with ruthenium hexamine decreases if the adhesion layer goes off. So that's another thing that you could try. Hopefully that's very helpful, George. Okay, I want to make sure I get to as many questions as I can. Okay, from Rangiku Matsumoto, san, probably. I'm imagining you're Japanese. Thank you for your series, very informative. What is the best way to determine the mechanism of a corrosion reaction using Tafel plots? I think I can help you with that. I am going to, if you give me 1 second, Neil gave a talk on this very topic. I'm going to see if I can find his slides. And so bear with me, because he talked a little bit. He gave an RRDE webinar, and I think I can gain access to it and find the slide that has to do with using. It just takes a little bit of time because his webinars are very long, which is okay. Corrosion reaction. So I know he has, for his talk, he usually uses Tafel analysis or a Tafel plot to determine the number of electrons transferred for a an ORR experiment. I don't know if we have exactly something for. Okay, so I'm going to. All right, so let me go back to sharing my screen, except I'll be sharing Neil's PowerPoint. Thank you, Neil. Hopefully you all can see this. So this was a talk. He gave a webinar, which is now accessible to Tier 2 members through our YouTube membership program. But you'll have access to this webinar. He goes through Kotecha-Levich analysis, and then he goes through Tafel analysis, goes through the Butler-Volmer equation, and ultimately he creates these expressions for the anodic and cathodic sides of Tafel analysis. And the big key takeaway was that when you're doing Tafel analysis, you end up getting this kind of slope. And when you have a different number of electrons, like n, if n is 1 or 2 or something else, you get a different number of electrons transferred, it'll change this B value. And so when you have something like, 120 millivolts per decade for the Tafel slope or 60 millivolts per decade for the Tafel slope, you get different numbers of electrons transferred. And that's usually sometimes utilized to look at corrosion, like what is the mechanism. And you can look at things like the number of electrons transferred for iron to oxidize. But let me also just stop. I want to take a closer look at the question. Is there another using Tafel plots? I just don't know enough about determining the mechanism using a Tafel plot. I know that Tafel plots might be really good at determining the corrosion rate. Other techniques like linear polarization resistance are used for determining the rate. I don't know per se how much of the mechanism, because the Tafel slope will give you a number of electrons transferred, and that is usually pretty helpful in and at least diagnosing what the mechanism might be. So I'm sorry I couldn't give you more information. Tafel analysis is still something I don't know a lot about, but I'm hoping that was kind of helpful. I'm going to try to move on to a couple other questions. Okay, so a question about impedance measurement corrosion testing. Can surface area of, this is from Gosia, I hope I got that right. Can surface area of the protective barrier layer, especially total, affect the resistance of this barrier? Yes. Well, will the surface area? I think the area by itself, maybe not so much. It's, I would say, the thickness of a protective layer will determine if the resistance is changing. And yes, if you use impedance spectroscopy, you will observe that the resistance is very high. But I think it's important to recognize it's the surface area with respect to the area of the whole system, sort of say. I think also in impedance experiments, because you are working with a potentiostat with limitations, you can't just have an infinitely large surface area. Because if you have a very large surface area, you also have more current that's passing. So you may have to make certain decisions about, okay, what amount of current is viable for making your measurements accurate. So hopefully that was helpful. And if you can provide me with a little more detail, maybe I can address your question a little bit more. Henri asks, electrochemical EC CO2 reduction is an encouraging approach for the production of value-added fuels or chemical production. I'm not so sure. There is chemical production. Actually, I kind of think chemical production, if that's the question, like electrochemical reduction of CO2, I think it actually may be better for chemical production as opposed to just value-added fuels, if that is the question. But I'm happy if you want to give me some more questions or more details about this. Kashif asks, I'm working on lithium-ion battery recycling in a filtrate of LFP battery, lithium, iron, phosphorus. Is there any way? Can we deposit it on any substrate by an electrochemical method? I don't know. I think it sounds like the things you're working with, lithium and iron and phosphate, there are techniques such as electrochemical deposition. This is usually like you have a positively charged metal, and lithium and iron can be that. And then you apply a negative potential to your electrode while stirring, and the iron and lithium will deposit onto the surface of your working electrode. But I'm truly not super familiar with lithium ion batteries, or perhaps even what the filtrate is. So I'm kind of making a lot of that up. Hopefully, Neil, I think maybe next week we'll be able to address some of those questions in more detail. I'm sorry, Kashif, but hopefully that was maybe a little bit helpful. All right, moving on. Let's see. Rangaku Matsumoto-san, about what you said with decreasing the solution resistance by decreasing current, since V equals I, since R is equal to V over I, wouldn't a decrease in current actually increase the resistance? So actually increase the resistance. Well, I was looking, when I was talking about that, I was referring to the voltage drop. So if you assume that the voltage remains constant, then yes, you are correct. If we decrease the current, there would be a you would say there would be, yes, an increase in the resistance if the voltage remains the same. But the voltage is the thing that is able to change. We're trying to decrease the IR drop. So So if I think about allowing the voltage, so I actually look at the equation as V equals IR. And if I want to decrease the voltage, I can decrease the current, or I can decrease the resistance. I can do those two things to get the voltage to decrease. So hopefully that adds a little bit more clarity to your comment. Okay. Matt Biang, regarding the EIS, if I am correct, AC resistance and DC resistance in a solid polymer electrolyte stand for high and low frequency response. Can you shed some light on that? AC resistance, high and low frequency. I think I might need a little bit more details about what you're asking for. So Matt Biang, I think we talked a little bit about this at the last in the last live stream, in the sense that the electrochemical system is the same regardless of the AC or DC techniques that are applied. And the AC resistance and the DC resistance, they're both resistances, sort of say. But AC allows you to adjust the frequency response. I don't know enough about a solid polymer electrolyte in terms of what its frequency response would be, but things to keep in mind actually have to do with some of the fundamentals of EIS, and how circuits respond to frequency. So I would encourage you, possibly, Neil has this webinar for tier 2 members. And the webinar series, it's a 5-part webinar series. Each one's like an hour long. It goes into a lot of detail, basics and even more detailed stuff about EIS. But a little taste is that we'll talk about the circuit elements, such as the capacitance, right? So you have capacitance in your electrochemical cell. Well, the impedance associated with capacitance decreases or is very, very low at high frequencies. And but a resistor, just if you modeled your system as a resistor, resistance does not have a frequency response, sort of say. So a lot of what you see in some of your systems from a frequency response has to do with, oh, I have some capacitive impedance because I'm getting more impedance, both imaginary, just total impedance magnitude, because of the capacitive elements in my system. And a solid polymer electrolyte just by itself may just be resistive as just a pure resistor. So it might not really have a frequency response. It's those interfaces between the solid polymer and other things that are going to give you some interesting results at different frequencies. Hopefully that was a little bit helpful. Okay. So let's see, to the best of your... Okay, so I'm going to address a question from one of our tier 1 members, Kempor. To the best of your knowledge, how can one mimic a potentiostat using only readily available electronic equipment? Okay, so readily available electronic equipment is, I guess, a somewhat broad topic, but let me, if I didn't have a potentiostat, and a couple of things that you might have in the lab would be something like, say, a battery or a power supply, and you may have a voltmeter. Okay, so I'll use I will share my screen to kind of show you some ideas. Of course, there are going to be limitations because there's just stuff that a potentiostat can do that these other instruments can't do. So in your electrochemical cell, I'm going to draw this to be fairly big, so I have lots of space to. This is your solution. Then I'm going to make things interesting colors here. So I'm going to have a working electrode here. Just make it like this. That's working. And then I've got counter. And then I'm going to make the reference red so that we know. And then I'm going to type all these in. So Chempor, hopefully you can, so I'm going to call this working, work, and then ref, and then counter. All right, so hopefully that's somewhat understandable, Chempor. Now, while you cannot do a cyclic voltammetry experiment or get the type of feedback that you can normally get with a potentiostat, you can do some electrochemistry by hooking these guys up. And I will use a little blue here. This works. So, or green, I guess. Okay, so I can use a power supply. So sometimes they use this symbol, like a battery, to drive a voltage across the working and counter electrode. And I can measure the potential separately with a voltmeter. So this is just like I'll just type it in here, voltmeter. So voltmeter here, you have power supply here. And you could make something kind of like this. You don't have to necessarily have these two connected to each other. You can have separate connections, but you would measure the voltage between these two electrodes. You would apply potential between the working and counter, but you would not have, say, the feedback mechanism to actually do the experiment. So I'm not so sure. Again, I don't know what readily available electronics are. But I'll tell you this: Pine Research does have potentiostats, and they can be purchased. And actually, you can purchase very inexpensive potentiostats. We sell, I don't know, maybe for $1,000 you can get a pre-owned one of our older model Wave Now potentiostats, and it'll do cyclic voltammetry. It won't be able to do things like IR compensation, but like for $1,000, it actually can run a lot of stuff. It can do like bulk electrolysis, cyclic voltammetry. It has a galvanostat, so it's still very powerful. Now I know I'm doing a lot of self promotion, but this is Pine Research, so I'm gonna try to sell our stuff. But hopefully that addresses your question to the best. That's to the best of my knowledge. How you can kind of mimic a potentiostat, like just in terms of what it does. So let me go to George Romo Rios from Brazil. Welcome. Thank you. Let's see if I can address your questions. I may or may not be able to. I'm developing a method to quantify sigma phase, so chromium-rich phase duplex steels in the linear scanning voltammetry technique using potassium hydroxide. Could someone please help me with an article explaining the mobility of chromium and molybdenum in duplex steels in alkaline media? How does surface roughness influence peak current values? Okay, so first and foremost, I haven't worked with these kinds of systems, so I'm not 100% sure. So to address your question regarding the mobility of chromium and molybdenum in the alkaline media, so you want to ask the question of how do these molecules, how do these ions, or maybe molecules, maybe they have stuff around it, how do they move in solution? And so if you do a technique like cyclic voltammetry, or even linear scanning voltammetry, it's hard, but if the chromium and molybdenum are solution phase, the current response that you get, say the peak current, might be related to the Randall-Sevcich equation. And you can find things like a diffusion coefficient. The diffusion coefficient is ultimately the thing that's going to help you learn or understand about the mobility of the chromium and molybdenum in the duplex steel in alkaline media. So my assumption is that the chromium and molybdenum have left the steel. They're not in the metal anymore, and they're floating around in alkaline media. And you want to know, how do they move? Now it assumes that chromium and molybdenum do something in the solution. And if they do, if they are electroactive, you will get some peak current associated with them. And you can use something called the Randall's-Sevcich equation. Let me look that up and then type that into the chat so that you're at least aware of what equation I'm referring to. I'm just going to send you to the Wikipedia page. Okay. Let's see. How chromium moved through the film formed on the surface. Okay. They move through the film. Okay. So there are some. So the key is to understand whether or not, when you do something like cyclic voltammetry, because really, like, if there's a film that's formed on the surface, you're looking at the diffusion of the chromium and molybdenum through the film. And if the film is very porous, or, you're going to get a very different type of diffusion coefficient than say, if it's just in solution, just in the hydroxide. I don't know if there's a way to really differentiate between film formed through the surface, mobility of the chromium and molybdenum through the film versus molybdenum and chromium through the alkaline media. I'm just trying to think a little bit about how that might work. Because I was going to think EIS might be a good way to do it, because there is a way to use low frequency, like using something like a Warburg element to determine the diffusion. I do believe EIS is actually the way to do it. So I'm going to throw Neil under the bus and say that's what you can do. And there may be a circuit model, because the interface, I'm wondering how you can get different information about the interface. I mean, it might be possible if you sandwiched, like, once you formed a film and you had a solid state thing and you actually sandwiched your electrodes together, maybe that, and had a 2-electrode system, that might give you some information, but I am not 100% sure. I'm sorry, George. But George, I think I can answer your other question about how does surface roughness affect peak current values. So if you have a very rough surface, that usually means you have a very large surface area. So the more rough the surface is, the more surface area you have. And surface area and current scale linearly with each other. So if the surface area increases, your current, and hence your peak values, are going to increase. Also, if you're doing, like, linear sweep voltammetry, I would imagine that your background current also increases proportionally. So just keep that in mind when you're looking at what your peak current values are. I hope that was helpful, George. Okay. Just looking at a couple. Okay. All right. There's a question from another Ramachandra, who's a member. Let's see, from a YouTube member. Can we couple EIS and CV together when characterizing a working electrode? If yes, what are points can be taken into consideration, expand upon? So you can, so first off, yes, you can couple EIS and CV together in the sense that you can do a cyclic voltammetry experiment and you can do an EIS experiment. You can get data from both of those, and you oh, George, I'm glad that you that was very helpful. Says you can look at the data of both of those for a working electrode to do some kind of, let's see, a couple of, when characterizing the working electrode. So so maybe I should clarify this a little bit more. Most of the time, EIS and CV are not, they only characterize the working electrode so much as the electrochemical system. So Ramachandra, let me see if I can clarify a little bit more. When you get a cyclic voltammetry, when you get some CV data, and let me just share my screen so that this might make it a little bit easier to understand. Let's see. So I figure out here, annotate, draw, blue. So I got a cyclic voltammogram, and it looks like this. All right. So this voltammogram, and I know it's not a beautiful looking duct because I can't draw, but this data has to do with the anolyte. It has to do with the redox couple. So this has to do with, this is like the redox couple. So that's what this data tells you, right? When you look at this, it doesn't particularly tell you very much about the working electrode specifically. Now, for example, alternatively, if you have a special electrode, let's say I did the same experiment, voltage, current, but I got something like this. Okay, so same voltammogram, but then I got this huge current. So I had one that looked very normal on, let's say this was a different electrode. So I had one that looked like this. Oh, sorry. This is actually supposed to just be. Let me just draw that again. That was supposed to be basically exactly the same, except it doesn't go up. It just maybe does this, and then this follows the other one. So hopefully you're with me on that. So this here, though, maybe sorry about using yellow. This actually tells me a little bit, like if the working electrode is different, then and everything else is the same, this usually tells me some information about my working electrode. Specifically, that for whatever reason, my electrolyte and my working electrode material are doing something here. Usually this is like hydrogen evolution if you have, or actually maybe water oxidation if you have like a platinum electrode, and this is oxidizing current. If you had a platinum electrode, for example, here, oh, this has to do with water oxidation. That tells me a little bit about my electrode. And maybe, maybe if I had the same thing and it was like this, and it just went up, then it's like, oh, well, this tells me that my working electrode is more catalytic towards water oxidation. I'm just making that up, but that's what the CV data will tell you. It sometimes doesn't always tell you about your working electrode specifically. It tells you about the redox information, and the EIS data itself, don't know that much about it, because it tells you information about the entire system, really. But yeah, you can, usually you'd want to do EIS at different potentials, see if you get different changes in the plots, different things are happening. Let me just see what Ramachandra's follow-up. What if the duct plot is the same for two different working electrodes with different dimensions and roughness? So I think the question would, so Ramachandra, I have two follow-ups for you. So how big of a difference between these working electrodes are there? So do these ducts line up on each other exactly? So for example, just like so, because there can be some experimental error, but like, are they exactly on top of each other? Or is there like a little bit of current difference between the two? And the roughness, I mean, it's rare that you'll get voltammograms that are like exactly on top of each other when you have two different electrodes with the surface area, with like, if the surface area, well, actually, let me think. Different dimensions and roughness. So if the duct plot is the same, so the main thing I'm curious about, Ramachandra, is that usually, yes, you can have a different surface area, and that changes the current a little bit, a very, very small amount, but not enough to make a huge difference. If the duct is the same on the working electrode, like the shape is the same, but the current values are different, then it just means the redox couple, it's homogeneous, the electron transfer and its kinetics and thermodynamics are independent of the electrode material. That's, in short, what it means. So hopefully that was very helpful. When I get to Kimpor's question, I'm also, guys, I'm going to preference, YouTube members, our members, for answering their questions more, but I will get to other people. Which is better, running a slow electrolysis at 10 milliamps of constant current, or using constant voltage at the redox potential? It depends what you want to do. It really does depend what you want to do. Sometimes if you want a reaction to just run really, really fast, if you're just trying to control a reaction, like bulk electrolysis type of stuff, typically doing it galvanostatically at, say, a constant current tends to be better, and you allow the potential to fluctuate. If you choose a constant voltage, it has the advantage, the constant voltage usually indicates that you won't create something that's not supposed to be there, but the constant current usually ensures that the rate of the reaction is always going on. So it depends a little bit on what you're trying to do. Let's see, Ramachandra, the peak potentials are different, though, not too different. If they're just a few millivolts in difference, just a few millivolts, even between 1 and 10, then it's probably within experimental error, because the reference electrode is different. Your reference electrode potential can shift a little bit between experiments. So that's I don't think there's any major difference. If there's hundreds and hundreds of millivolts difference between the potentials, then you have something different. Then you have more of a heterogeneous electron transfer, where the molecule undergoing the electron transfer, the current, so the molecule undergoing the electron transfer, it depends on what the electrode material is. All right, so hopefully that was helpful. All right, so Soltar had a question earlier. I think I can try to address it. Hello, Alex. I have a question concerning reference electrodes. What magnitude of current flows between reference and working? What changes in case of pseudo-reference? What's the main reason for pseudo-reference? And I think you had some pseudo-reference instability, and then you had some follow-up. Okay, this is the same thing. So let's just get Soltar's question. So the magnitude of current that flows between the reference and working should be minuscule. It should be tiny. Zero current should flow between the reference and the working electrode. Okay. Only a tiny amount will flow. And when I say tiny, I mean like 1 × 10⁻12 amps. Very, very small, because the resistance, a reference electrode is hooked up to what are known as the inputs of an operational amplifier. And the inputs of an operational amplifier in the potentiostat circuit have a massively huge impedance. So current should not flow into the reference electrode. And so there's no current that flows between the reference and working. Now, your question about, so I'm clicking some buttons. What changes in case of pseudo reference? So if you have a pseudo reference electrode, which it would be something like a silver wire, or that's like a quasi reference electrode, then of course that also shouldn't change the current that flows. But what's the main reason for pseudo reference instability? So the reference electrode instability for a pseudo reference electrode instability is that the potential of a pseudo reference electrode, of course, it's unstable because it's something like a silver wire, and the concentration of species around a pseudo reference electrode is not constant, right? It's changing. And so because it changes, its reference potential is unstable. Hopefully that makes sense. Let me know if you need some additional clarification on that. But the potential of your reference electrode, so a non-pseudo reference electrode, that reference electrode is encased in something like potassium chloride. So I can go to the drawing board and just show you, let's just take a look at what a reference electrode looks like from a construction design. So normally a reference electrode, we'll just do this very quickly. You have a wire. Sometimes you have some salt caked onto it. So this is like a silver chloride reference electrode. It's in a tube. I'm making this very big. And then there's a frit at the end. And then this whole thing is in solution. So the potential of your reference electrode is based on the Nernst equation. So potential is based on Nernst equation, which is E is equal to E naught, either plus or minus, like nRT, nRTF, or I think it's like, I'll double check, but it's just a constant times times the natural log of the ratio of the concentration of species. So let's just say oxidation over reduction or something like that of, those species. So in a reference, so the key is that all this stuff is basically constant except for this. When the concentration of species change, the potential changes. Reference electrodes are constructed in such a way that it allows ionic flow, but the concentration, what the reference electrode feels, is more or less constant. This is like a set number. So the pseudo reference electrode doesn't have any of this. Pseudo reference electrode just has the wire in solution, right? The pseudo reference electrode just has a wire. That's it. So anything, any species, drift, whatever, it feels it. And that's why the potential becomes unstable. I hope that was helpful. I hope that was helpful, Sultar. Okay. So let me just check a couple things. Rangaku, the 3 electrodes, let me just see, the 3 electrodes set up for corrosion studies. Why would there be more than one degradation seen on one side of the electrode? Why would there be more than one degradation seen on one side of the electrode than the other? Oh, why would there be, sorry, why would there be more degradation seen on one side of the electrode than the other? I would say, Rangaku Matsumoto-san, that it usually has to do with active sites, probably, because it's a working electrode. So whatever the working electrode is, and the exposed solution, the electroactive sites will be different than just the surface area. So for whatever reason, maybe there's more bends, more folds, more interfaces where corrosion could occur. That would be a reason why you see more corrosion or degradation on one side than another. And then Rangaku asks, can I take any art database, electrochemical studies, journals on electrochemical research? So the Electrochemical Society, usually Google, honestly, Electrochemical Society Journal. Journal of the Electrochemical Society has a lot of publications. I think they are sometimes good, sometimes bad. It varies. It's a gamish of stuff. So hopefully that's helpful. Rengaku. Ramachandra asked a question: can we have a rough estimate of peak current values for both anodic and cathodic just by looking at the CV itself? Absolutely. Yeah. When you look at the CV, yeah. I think, yeah, you can have a rough estimate. So if you, you're in Zoom, let me just share my screen again. Okay. So we draw, so it's red this time. This is current. This is voltage. This is the CV wave. Okay. So like there is a background current, right? So if this is 0, there is some background current here that needs to be subtracted, right? So when if you have this 0 just all the way through, you've got this background current that should be removed. And this isn't a great drawing. But if this background current is really, really small, if you just look and just eyeball this area, this value is the peak current. And similarly, you got some double layer here, but I think you can do a rough estimate. It's like, yeah, that's the peak current for cathodic and anodic. So you could easily just look at those values, and that's the peak current. I hope that was what you were asking for. And that's just by looking at the CV by itself. Okay, so let me stop sharing and then go back to see. Some water. Okay, so Matt Byung, Alex, is there a way we can clean the frit? One of our scholars allowed by mistake dissociation of the working electrode, and frit was completely darkened by working electrode particles. Okay, so what you can do, it's a little hard. Here are some ways people have cleaned frits, Matt. Some people have, and I'm assuming this is like an aqueous phase, silver chloride. No, hold on. Ramachandra, just quick. Can you expand on Randall substitution equation? Oh, all right. I can talk a little bit more. I can talk a little bit more about it in a minute. So Matt Byung, to clean the frit, some people have done a few things. Frits can be made out of a variety of different materials. A lot of them are porous glass. Some of them are other types of polymer materials, like Vicor is a pretty good one. Coropor, all kinds of stuff like that. But people have cleaned frits by exposing the frit to like concentrated acid, like sulfuric acid. One person, legit, no joke, said they used aqua regia to clean the frit, and that worked. I don't know if I'd recommend that, but that's okay, man. Yours is porous glass. Okay, that's good. So porous glass can take a beating, basically, but I would have it soak in something like hydrochloric acid. I would also, if you use a tank, like a gas tank, and you have your electrode full, fill your electrode with, say, water. I wouldn't necessarily use acid, but I would use water, and I would blow air through it, applying pressure to force solution through the frit, right? So it's basically, the frits are always leaking, but now you are forcing it to leak at a much faster rate, okay? And that's a way you can clean the frit. Now, one thing to keep in mind is the important things about reference electrodes is that they must be stable. So whether the frit is clean or not depends. It shouldn't matter all that much. but the reference electrode must be stable because the chemistry that you're interested in is happening at your working electrode. So as long as the reference electrode potential is stable, you should be okay, regardless if your frit looks a little discolored. Of course, you can buy new frits and new reference electrode, but that's the first thing I would do. I would try acid washing and pushing solution through the frit. Hopefully that makes sense. All right, Ramachandra, can you expand upon Randall-Sebstich equation? Wait, hold on. Before we get into it, so asymmetrical degradation has to do with the electrode surface area directly. Then this is from Ragiku. Yes, I think it has to do with the electrode surface directly. Yeah. Details about the surface has to do with why things are degrading differently. That's my take. Ramachandra, can you expand? You're welcome, Matt. Can you expand upon Randall-Sebstich equation? And then same question with little difference. If we could judge peak currents through CV, will the same be applicable to peak potentials as well? Peak potentials. The potential at that peak current, yes. Because with CV you're scanning, left to right, but you're scanning the potential. When you see a peak, you can identify that voltage as the voltage at the peak current, right? So that's one thing. The Randall-Sebstich equation, I don't know all of the details about it, but I can share my, let's see if I have so let me share my screen again. And this time I'm going to share Wikipedia. So this is the Randall-Sebstich equation. This is from Wikipedia. The Randall-Sebstich equation, I don't know how it was completely derived or where it came from, but it basically just relates the peak current of the forward sweep in a cyclic voltammogram to some basically constants. Usually it's a 1 electron transfer, a number here. Faraday's constant, the area, the bulk concentration of your species. Again, number of electrons, Faraday's constants, the scan rate, which is nu, the diffusion coefficient, and temperature, and that's the gas law. The Randall-Sebstich equation was probably derived from, a lot of the equations in electrochemistry come from differential equations or partial differential equations of electrochemical systems with boundary conditions, and then using Laplace transforms to basically come up with an equation. So at the peak, this equation is valid for the current. Is basically what it comes down to. And let's see. Peak potentials are still, you can still use the same values. Absolutely. Just make sure your values are correct. But I hope that is enough of an expansion, Ramachandra, on the Randall-Sebstich equation. It's a mathematical equation. It just relates that peak current to all of those values. It's mostly used when you know what the area of your electrode is and you know the concentration. You can usually determine a diffusion coefficient, and people will do scan rate dependent tests, correcting for the background current because the background current changes, and then using those peak currents, doing a linear regression to then determine what the diffusion coefficient of your molecular species is. So I hope that was helpful. Okay, so Aswin Raj, can I use my silver chloride reference electrode to do experiments at 8 degrees? Will it damage it? I want to perform LSV. So it's very funny you mentioned this because I actually did run into an issue with this. Here is the issue with using the silver chloride reference electrode at 80 degrees C. First off, yes, you can. But if you're doing a temperature dependent study, what can happen is if you do an experiment multiple times and you heat and cool and heat and cool and heat and cool your reference electrode has saturated potassium chloride in it. Every time you heat up the solution, you evaporate some of the water, and then you create you create a precipitate of potassium chloride. That potassium chloride can block the frit. So that is something you must be very, very careful about, because you do run the risk of blocking the frit with a silver chloride reference electrode at 80 degrees C. I know this because it happened to me. So Astrid, I hope that was helpful. If you want me to elaborate on that further, please let me know. But just one experiment at 80 degrees C shouldn't be a problem. And one thing we now do, because we ran into this problem where the reference electrode was kind of unstable at those higher temperatures, is we used a salt bridge. We used the salt bridge to have the reference electrode in one spot. And let me I'll show you a picture of kind of what the salt bridge looks like. Give me 1 second. Hold on. So I'm going to share my screen in a minute. Okay. All right. So this is what the salt bridge looks like, which is this. So this is from Pine Research. So you have your electrochemical cell on one side. There's like this fritted tube. There's a fritted tube here, and then it goes all the way to another cell with my reference electrode. So this is a way of isolating your temperature study from your non-temperature related study. So this is a salt bridge kit that is purchasable at Pine Research. But that's another way, if you're worried about damaging your reference electrode, you can get a salt bridge to help with that. Okay, let me get back to Zoom. Okay, Ashwin is also asking, is there a workaround? Can I change testing color after each experiment? So you can, but you'd have to make sure that the potassium chloride, it's stable, right? And so that might take some time to make sure that the potassium chloride and stuff is stable. You can still use it. I mean, it's fine. It's like when we ran into the problem, it was after multiple uses of cycling the temperature on and off, on and off, on and off, that we crashed the precipitate inside the frit and blocked the electrode. So that's the only problem. But yeah, if you change the solution, if you watch it, here's an important thing: do an open circuit potential experiment before you do your CV. And if your reference electrode's blocked, the OCP will tell you basically that it's blocked. It'll be at an extreme, like plus or minus 10 volts, or it'll be at 0, right? That's what I like to do. Okay. Okay. Matt Byung asks, regarding LSV, why should we perform LSV if we can just perform a single segment in CV? Matt Byung, you're correct. They are the same thing. I think maybe LSV historically came first, so it was given a technique name. But cyclic voltammetry you're right. Cyclic voltammetry, a one segment cyclic voltammogram is an LSV experiment. So you're right. This is just part of all of the jargon associated with electrochemistry. Okay. So I hope that was very helpful. I'm just going to do a quick review. If you have any further questions, let me know. I'm just going to see if there was any questions that I missed, but I'm pretty sure I talked about everything to the best of my knowledge. And my hope is that next week, I might not actually be doing the live stream next week. Neil might be doing the live stream next week because I might be out, but we'll see what happens. I think I got just about everybody. Well, if that's the case, thank you all for showing up. We really appreciate it. If you have any further questions, again, like, comment on this video. We'll have the live stream up later at some point. So thank you for joining us, and we're hoping to do this more often. Okay, take care, and